A little after 5 in the morning, while most of the Texas Panhandle was still asleep, the ground did something it hasn't done in this exact spot in more than 100 years. It didn't tremble gently. It didn't produce the kind of faint, easily missed shudder that occasionally rattles a coffee cup somewhere in the middle of the country. It hit hard enough to wake people up from a dead sleep, hard enough to be felt not just across the Panhandle itself, but more than 100 miles away in neighboring states, hard enough that within hours, the United States Geological Survey confirmed something genuinely remarkable. This was the strongest earthquake ever recorded in this specific region since record-keeping in the area began. And almost immediately, before the aftershocks had even finished rattling through the plains, a very specific, very pointed question started circulating among scientists. And it wasn't simply what happened. It was, why did this happen here, in a place that, according to everything geologists understand about how earthquakes normally work, should be one of the quietest, most seismically boring stretches of land in the entire country. Let's start with exactly what happened, because the specific details matter enormously for understanding why this event has captured so much scientific attention so quickly. At approximately 5:21 in the morning local time on Thursday, July 23rd, a magnitude 5.0 earthquake struck the Texas Panhandle, with its epicenter located roughly 24 miles northwest of the small town of Miami, Texas, and about 24 miles south-southeast of the town of Spearman. According to the United States Geological Survey, the quake originated at a relatively shallow depth of approximately 3.5 miles below the surface. That shallow depth matters quite a bit in terms of how the earthquake was actually experienced by people on the ground, because shallow earthquakes tend to produce more intense, more widely felt shaking at the surface, compared to earthquakes of the same magnitude that originate much deeper underground. This is exactly what played out here. Residents across a strikingly large area reported feeling the tremor, including in Amarillo, Lubbock, Oklahoma City, and Tulsa, Oklahoma. Reports of the shaking extended even further than that, with people describing noticeable movement as far away as areas near Kinsley, Kansas, roughly 200 miles from the epicenter, and residents across western Oklahoma, including communities as far east as Lawton and as far southeast as Wichita Falls, and even areas near Oklahoma City itself. Hundreds of people submitted what the United States Geological Survey calls Did You Feel It reports, a crowdsourced system that allows the public to describe their personal experience of an earthquake's intensity in a given location, and those reports poured in from across an enormous stretch of the southern plains within just hours of the event. As of the most recent updates, no injuries and no significant damage had been reported, and officials noted that while aftershocks remain possible following an earthquake of this size, none had been reported immediately following the initial tremor. To understand why a magnitude 5.0 earthquake on its own generated this much scientific interest and this much public attention, you have to understand two things simultaneously: what that specific magnitude actually represents in practical terms, and, more importantly, exactly where this earthquake occurred, because location is really the heart of why this particular event has scientists paying such close attention. On the standard scale used to measure earthquake magnitude, a 5.0 is generally classified as moderate. According to seismological research from institutions like Michigan Technological University, earthquakes up to around magnitude 5.4 are frequently felt by people nearby, but typically don't cause major structural damage, and researchers estimate that roughly 500,000 earthquakes of this general magnitude range occur somewhere on Earth every single year. In isolation, a moderate earthquake happening somewhere on the planet is, statistically speaking, an almost routine occurrence. What makes this specific event genuinely unusual isn't the raw magnitude number by itself. It's the fact that it happened in the Texas Panhandle at all. Here's why location matters so much in this particular case. The vast majority of earthquakes that occur anywhere on Earth happen at or near the boundaries between tectonic plates, the enormous, slowly shifting sections of the Earth's crust that make up the planet's outer shell. Where these plates meet, grind against each other, collide, or slide past one another, enormous amounts of built-up stress periodically release in the form of earthquakes, which is precisely why regions like California, Japan, and the entire Pacific Ring of Fire experience earthquakes with such regular, predictable frequency. The Texas Panhandle sits nowhere near any of these active tectonic plate boundaries. It's located deep in the interior of the North American continental plate, far removed from the kind of active plate boundary geology that produces the overwhelming majority of the world's seismic activity. As multiple outlets covering this event have noted directly, citing seismologists' own explanations, earthquakes of this magnitude are considered unusual specifically because of the Panhandle's distance from major tectonic plate boundaries, where most seismic activity around the world actually occurs. This is precisely the detail that transforms this story from a routine regional news item into something that legitimately caught the attention of the broader seismological research community. To put the historical rarity of this specific event into proper context, it's worth looking directly at the actual seismic record for this region. because the numbers here are genuinely striking. According to United States Geological Survey data, Thursday's magnitude 5.0 earthquake was the strongest earthquake recorded in the Texas Panhandle since at least the year 1900, and it stands as only the fourth earthquake of magnitude 4.0 or greater ever recorded in this specific region across that entire 120-plus year historical record. For comparison, the previous notable earthquakes on record in this exact area include a magnitude 4.9 event back on July 30th, 1925, in Carson County near the town of Panhandle, a magnitude 4.5 earthquake on March 12th, 1948, located about 11 miles north of Dalhart, and another magnitude 4.5 earthquake on February 15th, 1974, roughly 9 miles northeast of Perryton. Thursday's earthquake didn't just add another entry to that short, sparse historical list. It topped every single one of them, becoming the largest earthquake this specific region has produced in more than a century of recorded seismic history. Some coverage of the event, including reporting from the Washington Post, described it as appearing to be the biggest quake in the region in more than 70 years. A framing broadly consistent with the historical record showing just how rare an event of this magnitude genuinely is for this particular stretch of Texas. So, given that this region sits so far from any active tectonic plate boundary, what actually causes earthquakes here at all? This is where the scientific investigation currently underway becomes genuinely interesting, because there isn't a single, simple answer, and researchers are actively working through multiple possible explanations rather than pointing confidently at one clear cause. Seismologists have explained that earthquakes in this general region can occur when accumulated stress causes ancient, dormant underground faults, fractures in the Earth's crust that may have formed millions of years ago and have remained largely inactive ever since, to suddenly shift and release that built-up pressure. These ancient fault systems exist scattered throughout the interior of continental plates all over the world, remnants of geological processes that occurred long before humans existed to observe or record them, and while they're generally far less active than plate boundary faults, they can still occasionally produce genuine earthquakes when stress within the surrounding crust reaches a sufficient threshold to trigger movement along one of these old fracture lines. But there's a second, considerably more complicated possible explanation that researchers are simultaneously investigating, one that touches on an issue that has become an increasingly prominent and increasingly well-documented part of Texas's broader seismic story over the past decade: the potential role of oil and gas operations, and specifically, the underground disposal of wastewater generated through those operations. This isn't a new or speculative concern invented in response to Thursday's earthquake specifically. It's a pattern that has been documented, studied, and directly linked to increased seismic activity across multiple regions of Texas for years. To understand this connection, it helps to understand the basic mechanics of how oil and gas extraction, and hydraulic fracturing specifically, actually generates the wastewater in question. During the fracking process, extracting oil and natural gas from underground rock formations typically brings up significant volumes of what's often called produced water, or wastewater, alongside the oil and gas itself, water that can be several times greater in volume than the oil actually being extracted. This wastewater, often naturally salty and contaminated as a byproduct of having been trapped underground in ancient rock formations for extraordinarily long periods, generally can't simply be released at the surface. So the common industry practice for decades has been injecting it back deep underground for permanent disposal through what are called injection wells. Multiple peer-reviewed scientific studies, including collaborative research from the United States Geological Survey and the University of Texas, have found that this practice of injecting massive volumes of wastewater deep underground can increase pressure on nearby previously dormant fault lines enough to trigger what scientists call induced seismicity. Essentially, earthquakes that wouldn't have occurred, or wouldn't have occurred with the same frequency or magnitude without this specific human industrial activity taking place nearby. This isn't a hypothetical concern specific to this one earthquake. It's a well-established pattern that has already played out repeatedly across other parts of Texas in recent years. And understanding those precedents helps explain exactly why scientists are treating the possibility seriously here as well, even while officials have been careful to emphasize that determining the actual cause of Thursday's specific event will require considerably more data and analysis before any conclusions can be drawn. In the region around Pecos, Texas, located in the western part of the state near the border of Reeves and Culberson counties, a magnitude 5.4 earthquake, at the time the largest, recorded in Texas since 1995, and the third largest in the state's entire recorded history, struck several years ago, and scientific studies subsequently linked the broader pattern of seismic activity in that specific area, directly to the underground disposal of contaminated wastewater from oil and gas operations. A 2021 study conducted jointly by the United States Geological Survey and researchers from the University of Texas concluded that the overwhelming majority of seismic activity that had occurred near Pecos over the preceding 2 decades was likely triggered by increased wastewater disposal specifically. An analysis conducted by the Texas Tribune around that same period found that earthquakes of magnitude 3.0 or greater had actually doubled across the state of Texas in a single year, a dramatic increase that coincided directly with the sustained large-scale practice of pumping hundreds of millions of gallons of contaminated wastewater underground every single day across the state's major oil and gas producing regions. More recently, and more directly relevant to understanding the broader regional pattern surrounding Thursday's Panhandle earthquake, similar concerns have been raised regarding a different part of Texas entirely, the Haynesville Shale Formation, a natural gas-rich geological region that straddles the border between East Texas and Louisiana. Just months before Thursday's Panhandle event, a magnitude 4.9 earthquake, believed to be the largest in Louisiana's entire recorded history, struck the Haynesville Shale region, and scientists strongly suspected that this quake too was triggered by oil and gas operations in the area, specifically wastewater disposal, combined with hydraulic fracturing activity. A United States Geological Survey seismologist directly involved in researching that specific event stated plainly that similar clusters of earthquakes in that broader region were induced by a combination of wastewater disposal and hydraulic fracturing, and that determining whether any individual earthquake is genuinely induced by human activity and identifying the specific cause, if so, requires a detailed, methodical scientific investigation rather than a quick or casual assessment. In direct response to that Louisiana event, the United States Geological Survey deployed additional seismic monitoring instruments in the affected region specifically to gather more detailed data capable of supporting exactly this kind of rigorous future investigation. All of this recent well-documented regional history is precisely why the possibility of human-induced seismicity is being taken seriously as researchers begin examining Thursday's Panhandle earthquake specifically, even though officials have been consistently clear that it remains far too early to draw any firm conclusions about this particular event's actual cause. Scientists investigating the Panhandle earthquake will likely examine whether changes in underground pressure associated with oil and gas operations in that specific area may have contributed to triggering the quake. But multiple officials quoted across various news outlets covering this story have emphasized directly that additional data will be needed before researchers can determine, with any real scientific confidence, exactly what caused Thursday's specific event. This is worth sitting with for a moment because it reflects genuinely careful, appropriately cautious scientific practice rather than either dismissing the possibility of human involvement out of hand or jumping immediately to a conclusion that hasn't yet been properly supported by actual data and analysis. Determining whether any specific earthquake was triggered by natural, purely geological processes, by human industrial activity, or by some combination of both requires careful examination of exactly where injection wells are located relative to the earthquake's precise epicenter and depth, how much wastewater has been injected in the surrounding area and over what time frame, and detailed analysis of the specific fault or fault system that actually ruptured, none of which can be properly assessed within the first few hours or even days immediately following an event like this one. It's also worth being clear and fair about the fact that natural, non-induced earthquakes absolutely do still occur in regions like the Texas Panhandle, entirely independent of any human industrial activity. And the small handful of historical earthquakes recorded in this exact area going back to 1925 predate the kind of large-scale, high-volume hydraulic fracturing and wastewater injection operations that have become so much more prevalent and so much more heavily scrutinized in more recent decades. Ancient fault systems, remnants of geological processes, stretching back tens or even hundreds of millions of years, exist scattered throughout the interior of essentially every continent on Earth. And while they release accumulated stress far less frequently than fault systems located directly along active tectonic plate boundaries, they remain entirely capable of producing genuine, naturally occurring earthquakes on their own, without any human industrial contribution required at all. This is precisely why the scientific investigation currently underway into Thursday's specific earthquake matters so much, and why officials have been careful not to prematurely assign blame to any single specific cause before the actual underlying data has been properly gathered, reviewed, and analyzed by qualified researchers using established, rigorous scientific methodology. There's an important, broader context worth understanding here as well, one that extends beyond this single earthquake and speaks to why induced seismicity has become such a significant, actively studied topic across Texas more broadly over roughly the past decade and a half. Texas sits atop some of the most productive oil and gas reserves in the entire world, and the state's oil and gas industry has expanded dramatically over the past 15 to 20 years, driven substantially by advances in hydraulic fracturing technology that have made it economically viable to extract oil and gas from geological formations that would have been considered inaccessible or uneconomical to develop in previous decades. That expansion has brought with it a massive corresponding increase in the volume of wastewater requiring underground disposal. And researchers studying this pattern across Texas have documented a clear, statistically significant correlation between the geographic areas experiencing the most intensive oil and gas wastewater disposal activity and the areas experiencing the most significant increases in seismic activity over that same general time frame. This has led Texas's own state regulatory body specifically responsible for overseeing the oil and gas industry, the Texas Railroad Commission, to become directly involved in investigating a number of these seismic events over recent years, including past earthquakes near cities like San Antonio, where inspectors specifically probed the potential connection between recorded seismic activity and nearby oil and gas operations following a significant earthquake event in that region. Understanding this broader pattern helps explain why Thursday's Panhandle earthquake, despite its moderate magnitude by strict numerical standards, has generated the level of scientific and public attention that it has. It isn't simply that a 5.0 earthquake occurred somewhere in the middle of the country, an event that, statistically speaking across the entire globe, happens with genuine regularity. It's that this specific earthquake occurred in a location where the entire underlying premise, the fundamental geological assumption that this particular region sits far enough from active tectonic boundaries to remain largely seismically quiet, has just been dramatically challenged by the largest earthquake this exact area has produced in more than 100 years of recorded history. Whether that challenge to previous assumptions ultimately gets resolved by identifying a purely natural cause rooted in ancient, dormant fault systems, finally releasing built-up geological stress, or by identifying a meaningful contribution from nearby oil and gas wastewater disposal activity consistent with the well-documented pattern seen elsewhere across Texas and neighboring Louisiana in recent years, remains a genuinely open question that will require careful, ongoing scientific investigation to properly resolve. For residents across the Texas Panhandle and the surrounding region in the immediate aftermath of Thursday's earthquake, the practical concerns understandably center on the possibility of continued aftershocks, and on understanding what, if anything, this event might mean for the safety of their homes and communities going forward. Officials have noted that aftershocks remain possible following an earthquake of this magnitude, a standard and expected pattern following any significant seismic event, as the surrounding fault system and crust gradually settle and redistribute stress in the hours, days, and sometimes weeks that follow an initial rupture. As of the most recent reporting available, no injuries and no significant structural damage had been reported as a direct result of Thursday's earthquake. A genuinely fortunate outcome given both the earthquake's shallow depth and the extraordinarily wide geographic area across which the shaking was clearly felt by residents. Looking ahead, the scientific investigation into exactly what caused this specific, historically unprecedented earthquake will likely continue for weeks or even months, following the same careful, methodical process that has characterized similar investigations into potentially induced seismicity elsewhere across Texas and Louisiana in recent years. Researchers will likely examine detailed records of oil and gas activity, and specifically wastewater injection volumes and locations, in the immediate vicinity of Thursday's epicenter, comparing that industrial activity data against the precise characteristics of the earthquake itself, including its exact depth, its specific fault mechanism, and its broader relationship to the region's known geological history. Additional seismic monitoring equipment may well be deployed to the area, mirroring the response seen following the recent Louisiana earthquake in the Haynesville Shale region, specifically to gather more detailed data capable of supporting whatever future scientific conclusions researchers are eventually able to draw with genuine confidence. Whatever that investigation ultimately concludes, Thursday's earthquake has already accomplished something significant on its own, regardless of its final officially determined cause. It has forced a fresh, direct scientific reckoning with exactly how well we actually understand the seismic behavior of a region long assumed to be among the geologically quietest parts of the entire country. A reminder that even landscapes with more than a century of largely uneventful, carefully recorded seismic history can still, on an ordinary Thursday morning in July, produce something genuinely unprecedented. Something significant enough to send scientists scrambling for answers and residents across 4 states awake and reaching for their phones before the sun had even fully risen over the Texas plains.